So this is our series of celebrating faculty success in the College of Engineering, which is a series of colloquia for our senior faculty, specifically those who are full professors in that rank for more than 7 years, and the intent is to kind of do these every 7 years. And it's the opportunity to give to senior faculty a chance to talk about their accomplishments, how they view their careers have been, and plan for the next phase. And today we have the pleasure of having Professor Jafvert, who is going to talk to us about his experience being a faculty member. And he is, of course, a faculty in in the School of Civil Engineering and in the Division of Environmental and Ecological Engineering. And his area is, of course, related to environmental engineering. And that's what he's going to talk to us about. All yours. Thank you.
Thanks. So here's my title. And some of you have seen parts of this before, so I won't dwell on that slide, but hopefully you can see this. So I started out here at the University of Iowa working with Richard Valentine doing chlorine chemistry. And so I wrote a computer program that had like 8 simultaneous ordinary differential equations and predicted the fate of chlorine when it reacts with the ammonia in water, which is critical for water treatment. Then I went to the EPA and worked with Lee Wolf doing some dehalogenation work on pollutants. How you put pollutants, chlorinated, brominated pollutants in soils, do they dehalogenate? And so I did that for 1 year as an NRC postdoc. And then I was hired by the lab and they said we need somebody to do distribution of organic acids in systems because we don't know how to regulate those. So 2,4-D, how does it absorb to soil? We don't know because you can't just use a KOW value for it. So I was at the EPA lab and the idea was well, we need information, we need quantitative structure activity relations on these compounds. So I started working there and worked with some of these people. So all of the people in green are students. Then the Exxon Valdez hit a rock in Alaska. And so somebody came in my office and they said, you want to work on oil dispersants. Oil dispersants are surfactants. So I started working on surfactants for a while, and I started at the EPA lab. And then after I came here to Purdue, I continued to work on surfactants for a while. And surfactants effects on pollutants, a little bit of emulsion work, predicting critical micelle concentrations, all sorts of things. And then I got back into this work because I had done some work on organic acids. With Linda Lee, we did some work on organic bases, the fate of organic bases in water. And Jose was one of my graduate students. He's now in Panama at a university there. Then I started doing some photochemistry. In fact, Wei Chu was actually up here because he was my first PhD student that graduated. And now he's got a faculty position in Hong Kong. But we did some photochemistry in micelles. So I worked in my surfactant chemistry and said, let's look at another environmental process, photochemistry, and mix the two. And then with Inez Hua and Tim Philly, we looked at other photochemical reactions, but often in sunlight. How do these compounds break down, not just in engineered processes, but also under sunlight? And we did a series of papers on flame retardants. And I started some work on sediment remediation because an industry came to Purdue and said we want somebody at Purdue to do this work, and I raised my hand and said, sure, I'll start it. So I'll show you why other people didn't want to do this work in some of my slides. With Linda Lee over in agronomy, we did some work on real-time monitoring. This was on hormones, and I'll show you a few slides on that work. And then more recently, fate of nanomaterials in the environment. So Tim Philly in Earth and Atmospheric Science here. Ron Turco over in agronomy was part of this. Howard Fairbrother is one of my co-PIs now at Johns Hopkins. He's in the chemistry program, so we've got chemistry, Earth and Atmospheric Sciences, agronomy, all. And Richard Zepp is at the EPA lab in Athens, Georgia. And with Larry Nyes, we're advising a student on water reuse also. And then point-of-use drinking water. In the global engineering program, I've been involved in point-of-use water treatment in rural areas in Colombia, and we're probably going to take that to Africa and other places. And so I'm back doing chlorine chemistry. So I've come full circle in what I've done. I haven't worked on chlorine for 20 years, and now I'm back working on chlorine chemistry because we're disinfecting water with chlorine, and we're trying to find very, very simple ways of monitoring chlorine. If you're out in the middle of Africa, you can't spend 15 cents on a stick to measure chlorine. You have to do it for like fractions of a penny if you want to disinfect with bleach. How do you know you have a residual chlorine concentration left over? So that's kind of where we're working now. So it's a different theme, but hey, it's still chlorine chemistry. One of my sort of, I guess, proudest achievements is the number of students I've been able to place in university positions. So when she was my first PhD student, Carolyn, he's in Hong Kong, she's in Taiwan, Fan is in Taiwan, C.C. Lin is in Taiwan. He's the one person I can't get a hold of anymore, so I don't know if he's still in this faculty position. Jose is in Panama at the Technical University of Panama. Tim did a master's with me, went on to Hopkins and worked for his PhD, and he's now teaching at the University of Illinois. This was a postdoc. Amanda was a postdoc. She was co-advised with Inez. Heather Gall was one of my PhD students who is now at Penn State, and Wen-Chi Ho just got a teaching job. He just started this fall in apparently, people tell me this is the second best environmental engineering program in Taiwan after National Taiwan University, right? So today I'm going to talk about research projects because really it's the students and what the students do. And so students were involved in all of these. I'll talk a little bit about my carbon nanotechnology work, the coal tar sediment hormones, and the water treatment. So to reflect on what I do, the best way is to show you pictures of me out in the field. So the first is carbon-based nanomaterials. This is actually a lab exercise. But the idea here is when the EPA started learning about carbon nanomaterials and companies got interested in putting carbon nanotubes in products, they said, are these things good or are these things bad? And the common way the EPA works on chemicals is they've got 60,000 chemicals they need to regulate. They have to come up with structure-activity relationships to predict how these compounds are going to behave in the environment, but also even toxicity. Should this compound be toxic or not toxic based upon the structure of the molecule? When you look at carbon nanotubes, you come back and say, I can't even measure this compound because it's not a compound. I can't put it through a GC, an LC, or anything else to be able to measure it even. It's not a chemical. It's a material, nanomaterial. So they got worried because it's like we can't even detect these things in the environment, let alone know about their environmental fate. So how are we going to regulate these things? So they started a big program, and the NSF actually was our first funder on this. But now currently we've got our second EPA project with Howard, and Richard has been at the EPA lab, has been cooperating with us on this, and Tim in Earth and Atmospheric Science. Tim's interested in fungal decay of these compounds because because hey, it's a large molecule. How do large molecules break down in the environment? By extracellular enzymes. What produces extracellular enzymes? Fungi. Fungi break down trees, so they can break down nanotubes too, if they have the right enzymes to excrete to nature to allow free radical attacks on carbon nanotubes and things like that. So the materials we worked with C60, unfunctionalized carbon nanotubes, functionalized carbon nanotubes, graphene oxide, and we've looked at solubility, direct photochemistry, indirect photochemistry, and some dark reactions with these materials too. And so this is the question is, well, we're going to be exposed to these things in the future? And the answer is yes, we're probably being exposed to these materials now. And it's like, well, are they safe for us to be using? Are they not safe? How long will they last in the environment? If we start producing these things in tons, are they going to go up in concentration in the environment and not go down because they don't break down in the environment. So the EPA is interested in, do these things break down in the environment? What are their products in the environment? And if they do break down, do they have effects on their degradation products in the environment? So we started with C60. And C60 it's this molecule without the oxygen. So it's basically a soccer ball. Every carbon on it is the same. It's at the apex of two C6 rings and a C5 ring. And it is fully aromatic. And this is a carbon atom, so the diameter here is very small, obviously. So it actually is not a nanomaterial. It's a molecule. I can actually put this through an LC and get a peak out of it. But the problem is it forms clusters. It forms nanoclusters of these molecules. And so it becomes a nanomaterial because I can have a cluster of buckyballs. And it is the basis, this structure is the basis of carbon nanotubes too. So if this thing breaks down with light, well, maybe other things. So we've done photochemical studies on C60. But these are pathways in organic solvents. The literature is rich. So in environmental engineering, what do? We go look up what the chemists do. We go look up what the biologists do. And we read their papers. And then we say, how does this work translate to what we do? Sometimes it translates well. Sometimes it doesn't translate all. So if you put C60 in an organic solvent, shine light on it, it does this. What's the one? So in photochemistry with sunlight, you have electrons in all your orbitals of all of your atoms. And those electrons have opposite spins, which is the fourth quantum number. So this one is plus 1/2, this is minus 1/2. And what happens is you shine light on that energy in the light energy is absorbed, and this electron gets promoted up into an outer orbital. So it has to because it just absorbed energy from the sun. And that's a singlet. And if this electron turns around and changes its spin number, now it's a triplet. And that electron can't come down because you can't have two positive spin numbers in the same orbital. So it stays up there for a while. It stays up there for a few nanoseconds before it comes down, but it stays up there for a little while. So now it's a reactive species, and it can bump into something else and transfer that energy to that other molecule, and then the electron comes back down, changes its spin down to the ground state. So photochemistry is amazing because you can do all of these reactions with photochemistry. It's like that is what I just told you is what happens to your blue jeans when you put them out in the sun. The dye fades. Why does the dye fade? Because electrons are being promoted up. That becomes a reactive molecule, and the dye molecule breaks down. Okay? But it requires electron transfer up into an upper orbital. Once it's up here, then this molecule can exchange its energy with oxygen. And it can make oxygen a singlet, which is actually the excited state. The ground state of oxygen is a triplet because the electrons are in different orbitals with the same spin, and in singlet oxygen, this electron comes over here, and now that molecule has more energy because the electrons want to be separate in different orbitals. And I'll show you that structure. So in organic solvents, you shine light on C60, it transfers its energy to oxygen, and now this is a reactive oxygen species. That reactive oxygen species can react with another C60 triplet to give you an oxide. That oxide can react with water and open up and give you hydroxylated fullerenes. Those are more water soluble, so the more I oxidize this, the more water soluble the molecule becomes, and now it can exist in water. It doesn't need to exist in these clusters in the water system. So the question, our first question was, well, does this happen in water? And there was a paper published just before we published our paper that said, no, you cannot produce singlet oxygen with C60 in sunlight. The person was from Georgia Tech. They did their studies for 2 hours. 2 hours is not long enough. The other thing you learn in environmental engineering is we're looking at long periods of time. DDT has taken 30 years to get out of the environment. So you don't look at short times in the lab. You have to extrapolate to long environmental half-lives if you're going to study the environmental fate of chemicals in the environment, because some take a long time. 2 hours in the lab is not always adequate to study lifetimes of environmental processes. So we were lucky, it only took 65 days. But after 65 days, these are C60 clusters in water. The size of the clusters goes down, and after 65 days, the color of the clusters even changes. And you get the mean diameter of these clusters goes down. So you can measure things about this. You can, since C60 is a molecule, we can actually measure its concentration too, and it decreases. So the next question is, well, is it singlet oxygen? Well, with singlet oxygen, like I said, this is the ground state. This is singlet oxygen, where this electron actually comes over here and flips a spin. So you can put furfural alcohol in, which scavenges singlet oxygen. If it scavenges the singlet oxygen, the furfural alcohol decays. So if you have furfural alcohol decaying, you know that you're producing singlet oxygen. And you can do a little bit of math and actually calculate a steady state concentration of singlet oxygen in the system. So here's C60 decay, here's furfural alcohol decay. These are just controls, dark controls, and if you remove the oxygen, you don't get the reaction occurring, which means it needs oxygen. So with furfural decay, it's like, yes, we're getting singlet oxygen in this process. Singlet oxygen is part of the reason why the C60 is being oxidized. So it was a nice study because we showed the mechanism for C60 decay in the environment, and we also showed that C60 with a little bit of light shining on it can decay in the environment. So we moved to nanotubes. Nanotubes are chicken wire, but you can roll up chicken wire different ways. You can roll it up so that you have, so I can roll it up so that this bond is next to this bond, or this bond is next to this bond. So I can roll it up at various angles. And the resulting angle here, like a 6,5 rolling up to the 6,5, gives me one nanotube with one size diameter with one angle. And if I roll it up a different way, I get an 8,1 or something like that. Well, some of these nanotubes are semiconducting. Some of them are metallic. Metallic means I can shuttle electrons through that conductive band really, really easy. The semiconducting ones, nope, they don't shuttle through, so they're semiconducting materials. So IBM is really interested. I showed you the slide, IBM. Hey, making the next generation computers out of carbon nanomaterials, because you can have semiconducting materials and you can have conducting materials. That means that they have different properties too, though. So now it's not just carbon nanotubes, it's like, hey, we got all sorts of carbon nanotubes here. If you put in a P3 carboxylated tube, so this is one specific, this is a carbon nanotube that has been partially oxidized to give it carboxyl functional groups on it, and you shine light on it, you can measure the furfural alcohol that's being produced. And here's furfural alcohol in water. Deuterium, heavy water, moves slower than water. Its molecular vibrations are slower. So as a result, the singlet oxygen that's produced has a higher, longer half-life in deuterated water than it does in pure water. So as a result, you don't get that singlet oxygen quenched by the water as much. It lasts longer, which means it has more time to react with the furfural alcohol. So in completely deuterated water, the furfural alcohol decays really, really fast because the lifetime of the singlet oxygen is faster. So mechanistically, we can show, hey, yeah, we're getting, again, we're getting singlet oxygen produced here, which, again, it's a reactive oxygen species. Reactive oxygen species react with other things, too, which means, you know, this is in sunlight, but we'll kind of get to that. Other reactive oxygen species, superoxide anion is one, which is oxygen with another electron on it. So how do we get this? If you excite carbon nanotubes and that electron can be shuttled to the oxygen, not just the energy, but the electron can be shuttled to the oxygen, now I've got a negatively charged oxygen molecule. These two compounds, NBT and XTT, are basically compounds that react with this very, very readily, and they give you a colored product. So you can detect whether superoxide anion is produced by putting in some of these scavengers or probe molecules in solution. Hydroxyl radicals, you can put in chlorobenzoic acid in the system to measure hydroxyl radicals in the system. And so when you get it all done and like a year later or 2 years later, the student comes back and you write the paper, this is what happens. You have carboxylated tubes or even pegylated tubes that shine light on it. The H nu is light. And you get an excited state molecule, which reacts with oxygen to give you singlet oxygen. But then it can eject an electron or transfer. It really doesn't get ejected, but it transfers an electron to oxygen to give you singlet oxygen. And there are many ways to get over here, but we can also measure hydroxyl radical in these systems. We can actually measure the accumulation of hydrogen peroxide in some of these systems too. So with a little bit of light, hey, we get all of these reactive oxygen species produced in the presence of carbon nanotubes, which now has an effect on the carbon nanotubes, but it also has an effect on other things because you're forming reactive oxygen species. Unfunctionalized tubes. So this is some work that SOMI is doing currently, which now we're trading our nanotubes out. Rather than using these ones that are functionalized, we're using unfunctionalized ones, just the chicken wire nanotubes. Chicken wire nanotubes are really, really insoluble in water. So you add surfactant. Hey, I'm back in surfactants now. You add surfactant to it to emulsify the carbon nanotubes into water, and they are basically unreactive in sunlight. They don't do much. But the question is in the environment, there are other sources of these ROS species. Can we get unfunctionalized nanotubes to react with ROS in the environment? So what SOMI did was she generated the hydroxyl radical by adding in hydrogen peroxide in her system, measured the steady state concentration of hydroxyl radical in her system, which is really low. These are environmental concentrations. So if you go out to a lake and measure the hydroxyl radical concentration, that's about what you get. So we're producing it at about that same rate. And then this again is a nanomaterial. You can't get it through a GC or an LC or any other instrument to detect the molecule. You have to use other methods. So this is near-infrared fluorescence. These nanotubes fluoresce. If you shine visible light on them, they fluoresce in the near-infrared range. And so this is where the 6.5 nanotubes fluoresce. The 8.4 ones fluoresce over here. And you do this in a radiated sample with hydrogen peroxide in. You can basically oxidize the tubes so that they lose their fluorescence signal. So we've reacted our tubes. And so in the environment, even though carbon nanotubes don't undergo direct photochemistry, they can undergo indirect photochemistry with other things. So this is her system. She's generating hydroxyl radicals. The surfactant itself could react. The nanotubes could react. And we get a bunch of other processes that could occur in this system. Another student, now we know nanotubes, electron transfer in nanotubes is important. So we said, can we do this in the dark? Do we need light to do this? Because we can add electrons other ways. So NADH is in everybody's cell. This is the main way energy is shuttled in all cells. NADH can give up electrons and form NAD+. And so NADH, if you add it to carbon nanotubes in the dark, the question is will you be able to shuttle electrons through the nanotubes to oxygen and form superoxide anion? Can nanotubes shuttle electrons in nature? And so here we're measuring superoxide anion by XTT and NBT. And yes, indeed, if you change the concentration of NADH, you get more superoxide anion out. If you do the right controls, you get nothing. So the difference here in the color that you see is due to the superoxide anion. This is important from a toxicology standpoint too. Because if you have nanotubes in your body, you also have NADH in your body. Nanotubes, and they've seen this, where nanotubes create the responses is for cells to actually try and put out more things that scavenge reactive oxygen species in the body. And so the question is what's the mechanism? And the mechanism, hey, nanotubes shuttle electrons. So they can shuttle electrons to oxygen in systems. They can shuttle electrons through other things. So if I have a good electron donor that may not react with this compound, I put a nanotube in between. The nanotube can accept the electrons and then shuttle it over to other things. So this is a potential toxicity mechanism for nanotubes in cells. So summary of the ROS generation in the dark. And one thing that is not on this slide is you generate this. We've looked to see, can we get DNA cleavage out of this? And indeed you can. You put NADH and carbon nanotubes in with DNA and you can cleave it. And it's because of the generation of these ROS species. So it's a potential mechanism for a toxicity of these materials, which the EPA is really interested in, obviously. So everybody's on the bandwagon. We have a whole nanotechnology center and everything else, which is great because nanotechnology is something. But you have to use them safely, and you have to know the environmental fate of these materials in order to be able to use them safely. What are the precautions that we should be taking when we're developing these materials? So I'll talk about coal tar contaminated sediment. I'm done with the heavy science. Now it's off to slides. This is in Hammond, Indiana. This is the Grand Calumet River. Over here is Lake Michigan. This is the Indiana Harbor and Ship Canal. And we're about, we can see Illinois from our site. This is a former manufactured gas site that produced gas in the early 1900s up to about 1950. They shut the site down in about 1950, but you still have oil in the sediment. So this is coal tar oil, which is mostly PAHs, naphthalene, pyrene, these ring compounds. Not unlike the buckyballs, which are fused benzene rings. These are ring compounds too. So you have oil in the soil. And so they were thinking, hey, this river, we've got water in here and we've got oil seeping from this. We've got oil seeping from the land. How do we remediate this? So our sponsor was the party that owned this, and they needed to supply data to the EPA to come up with a remediation strategy for this river. So the first thing that we did was we put in monitoring wells. Well, we sampled sediment, but we put in these piezometers. These piezometers go down 4 feet and 8 feet into the ground with a wellhead to measure the water pressure there. If you put this pipe down 8 feet into the sediment, the water level is up almost to the top of that, which means the water pressure is down there really high. Why are the water pressures high? Because this is a mile or two from Lake Michigan. You've got sand down there because this used to be the beach of the lake shore. So here's our piezometers, 8 feet, 4 feet, and then a river monitor. Date and head. This is 8 feet down, 4 feet down, and this is the elevation of the river, so you get storm events going on. So you've got sand down there. The sand is connected out, and you've basically got water flowing under the river and coming up through the river because this is a groundwater discharge zone in most cases. So in here, hey, this is clay that's about 12 to 15 feet down, very, very impermeable clay. Above that, you've got sand. We got this out of one of our piezometers. And above that, you've got this mucky soil that even has the oil in it. You can see the oil in here. So this is impermeable. This is sand, high hydraulic conductivities, moving water under it. That water's under high pressure. Where does it go? It comes up through this muck at a very slow rate because this is highly organic sediment underneath the soil. So we know that the water should be moving up. And we also know something about the chemistry here because we went out and measured the water phase concentration, sediment concentration. Just to give you an idea, this is naphthalene. This is 2 grams per kilogram. So 2,000 milligrams per kilogram is, and up to 16 grams per kilogram of naphthalene in the sediment because we got oil there. It's an oil system. So you've got all these PAHs in the system, high concentrations of PAHs. So we know the water's coming up, but we don't know the rate of the water coming up through the sediment. So how do you measure the water coming up? Well, you have to measure it somehow. So people were developing these seepage meters. You put a dome on the sediment, push it in a little ways, And this tube goes all the way up to the water, so it's above the water, so water can't come out here. The water has to come out of this tube. So if we've got water coming up through the sediment, it all has to go through this tube. We hooked this up, which is our flow tube, and the water has to flow through here. This is a heater, and these are thermocouples. So we heat the water in the center of the tube, and that heat then moves either out towards the river, which means water is coming up, or it moves in towards the tube, which means water is actually going down into the ground here. And we can measure the direction. But if we calibrate our meter, we can actually measure the velocity of water flowing through the tube, which means we can measure the velocity of water coming up through the sediment. So it's all computerized. Here's our lab in the field. And we hook this up to this. We measure the heat at these resistors. The temperature change is less than 1 degree centigrade at these thermocouples, so it has to be very, very sensitive. And you can measure the flow of water. So with those pressures and with the flow, we can calculate the hydraulic conductivity of our sediment. And we know now that the water's coming up about, the Darcy velocity is about 1 centimeter a day, which means it's moving at about 2 centimeters a day through the sediment. So the reason that they wanted us to do this study is because they wanted to put a sand cap on. Sand caps basically take the old benthic zone, the sediment where the organisms are supposed to be growing and living, the worms, you know, and the fish eat the worms and everything else. Now you put sand on top of it. So you remove the contaminants from the new clean sand. But if I've got water coming up through here with organics in it, how fast am I going to recontaminate my new benthic zone and contaminate it with these organic compounds that are coming up? So that's the purpose of this. We know how fast the water's coming up now, and we know the contaminant concentrations, so we can predict the contaminant concentrations. But what other processes go into it? So this is a 4-foot by 8-foot sheet of steel that's rolled that weighs about 80 pounds. And so when you write a proposal and say, we're going to take these 80-pound cylinders and we're going to push them into 4 feet of sediment, you know, I don't think this could be funded by NSF because somebody on the committee would say, no, you can't do this. It's just impossible. But this was an industry that sponsored us, and they went, hey, let's try it. You know, let's go out there and try it. So that's what we did. And we got these things in. We just put it through boats, stood on the top of this, and pushed these cylinders in. We made our own little sand caps. So we excavated down 2.5 feet, and we put a geotextile liner here, and we put some adsorbent material here, or do we just use sand? Here's our clay down here, or here's our sand lens, and this is all muck. So we're excavating about 2.5 feet of the sand, and we put a collar on it so we wouldn't mess up the rest of the water, and took that upland with the rest of this stuff, put sand in here, put we used a organoclay in some cells, we used peat in other cells as adsorbent layers. So we did 8 of these tubes. And here's a geomembrane that we lay down before we start putting sand in these things. So you prepare these things, then you start collecting data. Oh, so here's me next to one of these barrels. So, and here's a GC trace of the contaminants in the sediment. You put in monitoring systems. So we put in these sample ports so we could take samples below our adsorbent material, above our adsorbent material, and we put in piezometers to measure the water pressures to see if there was any difference above and below our adsorbent material. And once you get enough sand in the bottom, then you just pour the rest of the material in, remove the collar and pour it in. So here's data. This is concentration on this axis, this is depth. So about 70 centimeters below where we're collecting our samples, at the bottom of our sand, we have naphthalene at about 7 milligrams per liter. By the time it's up at 18, there is nothing. This was in 2008. You can't even measure it at the top. The naphthalene's coming up through here. We know that because our water is coming up through here. So what's happening to our contaminants? Well, we've made a nice sand cap that has bacteria in it. It's got diffusion of water and oxygen along the top. And so Layla and Larry Nyes, hey, naphthalene dioxygenase, phenyl hydroxylase. We've got enzymes in this cap that break down these compounds. So we're getting a biofilter, basically. The next year, the concentrations near the top went up a little bit, but I think it's because we were getting enough recontamination because we've got this nice sand cap surrounded by contaminated sediments, and we're getting a little bit of deposition of these contaminated sediments on the top of our system. But it's a good biofilter. It's interesting because when the EPA designed sand caps, they don't consider biological decay. They only consider adsorptive capacity. So how much organic carbon you put in, that's how much, that's the barrier. So the lifetime of it is by this. The interesting thing is they still design by the adsorptive capacity of how much carbon they put in their cap, but without considering biological decay. But when they originally started this, they had no idea of how fast the water was coming up. So once we gave them that information, then they had to go back and redesign their cap material to make sure that they had enough capacity for the next 30 years to absorb these contaminants. So this is full scale. So the IDEM, $33 million from the Great Lakes Legacy Act to remove sediment from about a mile of river of the Grand Calumet River. And they removed the top section of it, and then they put sand on it. So how do you design a sand cap? You need to know the flow rate coming up, and you need to know the contaminant concentration in the sediment, and you can predict the aqueous phase concentration from the sediment concentration, from partition coefficients and things like that. So they use some of our data to do this. Oh, and this, what is this? This is me in China putting in gravel next to a rice field, because biofilters work every place. They don't just work in northern Indiana. It's like you got tons of nitrogen and phosphorus coming down here. So how do you remove nitrogen coming down here? You put in basically a constructed wetlands. Although this is too small, so at base flow it would treat some of the water. High flows, this is too small, but at least for a student project working on this to see at low flows how effective is our biofilter in this system. So even in China, I've been throwing gravel in ditches. Hormones. Hormones in water. This is a project with Linda Lee, and Heather graduated, several years ago now, I think. But she helped me instrument this site, so I've been out in the field a lot lately. These are two ditches that drain, produce cattle barns, dairy barns, swine, sheep, aquaculture center. We put in 1, 2, 3, 4, 5, 6 sites. This one has 2 monitoring stations because one is monitoring a ditch and one is monitoring the stream. So that's 7 sites. What do these things look like? This has an ISCO sampler. It's got a data logger here. It's got an antenna with a radio to send wireless data back to the aquaculture center so you could see the data in real time online. And we wanted to do this basically so we could see the hydrographs in real time back on campus. Some of these sites like this one we changed because we needed to put a little wing dam in down here so that the water level was always above our flow meter so that we could monitor flow in the tile drains. So we're monitoring flow to see what the flow is. Part of the reason for this is because everybody goes out, grabs samples, and measures hormones. But what we wanted to do is do a mass balance of hormones coming off of the fields for an entire year. That means that you have to monitor on storm events and collect the hydrograph plus collect samples over each of those hydrographs. And so we had all of these sites, and after a while we could measure flow. We measured flow. The data logger monitored the flow then, but also we programmed the data loggers to collect samples at specific times. Why did we put it up on the wood? Because this is what happens during a storm event. So at this time, this pipe is flowing full off of this field. Here's Heather, and one of the sites was an old USGS gauging station that had a weir, so all we had to do is monitor the water level behind the weir. It's a calibrated weir. And then our antenna is on the aquaculture center to collect all of the data. In all cases, we powered these with solar panels, except at the USGS station, which had power. So her first thing was when do we sample to make sure that we have enough sample data points to predict concentrations. So the hydrographs look like first order decay. So if you measure a couple hydrographs out in the field, you get an idea of what that profile looks like. We also realized that, well, we can just sample as our flow gets to be a certain value. So let's just sample on this rising hydrograph at specific points because we know what the maximum flow is at most of these points. So we just increment that, so we collect about 6 sample points as the hydrograph is going up. And then we model this so that we can calculate how many, and so in this case she's got, I don't know how many samples here, but if we only had 5 samples left in our ISCO and it's a Saturday afternoon and the student doesn't want to go out there, it's like, what do you do? Well, the ISCO, the data logger knows how many samples it's already sampled. And it knows what this hydrograph is going to look like. So it divides the hydrograph up into 5 equal areas under this hydrograph to be able to know when to sample so that we don't run out of sample bottles during any hydrograph. And then if a new hydrograph starts, it starts all over again. So here's a case where we had a hydrograph on top of a hydrograph, and these are our sample points that we collected over these hydrographs. This is, the blue line is flow. This is orthophosphate. So you can see the orthophosphates coming out with flow. This is what happens with the hormones too, unfortunately. High flow, high hormone concentrations. So if you sample here, here, and here, you're going to miss the concentration. You have no idea how much hormone's coming out. So you really have to integrate the area into all of these curves in order to get out what's my flux of hormones coming off of the field that are going to end up in the Wabash River. So you go nuts and collect data. So this is just some of the data. And this is just some of the hormone data at one of the sites showing different hydrographs and showing the profiles of concentrations. Low flow, not much hormone. High flow, lots of hormones coming out. Which means if you're an agricultural engineer and you're designing best management practices to treat concentrations of hormones coming off of the field, most of those best management practices treat this flow. This is too high. They can't treat it. But that's what they need to treat, which means now you have to go back to management practices on the field, not in-site treatment processes to treat these hormones, unless you're going to capture the whole flow with a wetlands or something like that. So I'll skip that in the sake of time. So you do, even out in the field, you do a lot of calibration. You know, we set up these sites. We had to measure the flow, come up with our own rating curves for these sites and everything else. It was basically a 3 to 4 year project that every Friday afternoon, Heather and I were out in the field doing something. This is the point, this is a river in Munich. 2005, they attained the goal of bathing water quality in the Ishtar River. Not many people swim in the Wabash River. But it is possible other places to improve water quality to the point where, hey, you can do things with the river. The rivers are a huge source. Look at the number of people here that are down at the river swimming at this place because it's safe to do it. So, you know, it's like if we improved our water resources, we could do this in certain places too. So I'll go through these last slides really fast. But this is the fun project. This is the Columbia project where I'm working with a global engineering program to put water filters in some of these schools in Columbia. Here's Medellin, and we're working just north of Medellin over here. And these are some of the school kids in one of these small little rural schools. This is what Barbosa looks like. Barbosa doesn't have a neon sign in it. It's a town of about 6,000. They have a Kimberly-Clark plant. That's the main employer in the town. And I love Barbosa. It's a cute little, it's just wonderful. Barbosa is here. There's 38 little villages outside that the municipal government controls or runs the school districts in those. So some of these districts have high schools, some of them like Buga and La Planta and Graciano only have elementary schools. These elementary schools have generally about 20 kids that are like 7 to 13 years old in them and one teacher. This is one of the schools. This is a school at Buga. This is their water source. This water comes in from the mountain stream. It goes in here, it's stored, and then it goes directly to the faucets in the school. There's no treatment. You can see the mold growing on the water tank here. So that's what they use to flush the toilets. They take that water and they boil it to prepare food and to drink. So that's their food, that's their water source for these rural schools. Slow sand filters, these are 3 previous designs. Cement, you got to make it. It's difficult. Hey, plastic is a little bit better because you can move these barrels any place, but you can't stack these barrels. Once I put this barrel down, it's not moving because sand has a huge density, so that thing is really, really heavy. These are really heavy too, and they are wobbly, but these are international aid filters. The tube is outside, taped to the bucket, not a very good design. All of these have gravel in the bottom of these buckets. You put sand in, put gravel in the bottom, and you have a tube that comes out so that these tubes are all coming out below this level. So you can fill this up with water. The water flows through here, and then it flows up through the tube and out. So you feed these things up to 3 times a day with water, and then you get clean water out because it's a biological filter. The same thing happens in here is happening in the Grand Calumet River. You got bacteria in here that are eating up organic material. So the organic material, the colloids that are in the river water that are causing the color and the turbidity, the bacteria in these filters are metabolizing it and forming CO2 and water. So you put water that is got a lot of organics in, and what comes out is CO2 and water. So these are our sand filters. We decided I want to be able to carry this or move it. So it's a 5-gallon pail. I can buy a 5-gallon pail any place on the globe, probably even in Antarctica, you know. This is the Wabash River water. This is what the water looks coming out of this filter. The water, again, you pour it in, it comes down to the porous plate, comes up, goes down again and up. And so you can put about 10 liters in one of these because the retention, the void space in here is about 5 liters. You let the water sit. You pour it in, let it sit in there for 8 hours, then you pour the water in to replace the water that you just put in 8 hours later. So it's a batch reactor. The first time we did this, we did it like everybody else. We put gravel layers at the bottom, and so I had 3 students down there washing gravel and sieving gravel. And we put the filters together. Here's all of our gravel, but the reason for the gravel is you can put a tube down here with large holes in it to collect the water from it. And it works. It's just that it's not easy to sieve all of that material. So here's one of the students, or one of the groups, one of the schools that we were first at. This is, these 2 people are from the city of Barbosa. Maribel is from Kimberly-Clark. This is a teacher at the school explaining us about her use. We went down and saw 12 months later, we went down again to see how these things were working. She was still using it. She liked our filter. We've done chlorine demand tests on it, E. coli plate tests going into the filters, coming out of the filters, and then after disinfecting with chlorine. They still boil the water because it takes away the turbidity, improves the water quality, but it is not meant to disinfect, but you can disinfect with chlorine after that if you want. So teachers, government people, students. And so these are some of the students in one of the schools. We've gone from gravel to this porous plate, to this porous plate, to this porous plate. So now our porous plate I make in my garage, just out of plastic, high-density polyethylene beads. Sieving sand, we sieve sand for 3 days to prepare buckets for 15 schools. That's 60 buckets of sand, that's 5 gallons each, that's a lot of sand. We came back and we said, well, we needed to get rid of the gravel and do the porous plate, we got to get rid of these sieves. These sieves are killing us. So the next thing is you make a trommel. So you can take the trommel apart, the fine materials coming out here, the coarse materials, so we can sieve the sand to the right sizes. So students in the global engineering teams have built these things. And we're taking one of those trommels down to Columbia next week, actually. So the teachers put their hardware on their buckets so that they knew what the buckets would look like or what parts were there. We supplied them with the sandbags, and all they needed to do is pour the sand in once they got back to their schools and then start pouring water through them. So here's the group of the teachers that got buckets. We had 15 schools that got buckets the last time. And the teachers were from these different outlying areas in the area. So we marked the school teachers and the community leaders that came to our little workshop for this. And unfortunately, they had a teachers meeting the week before we went down, and they all talked about it. And so we had about 10 teachers show up that we couldn't give filters to because we only invited 15 teachers, and we got about 25 teachers showing up. So this is water going in. This is water coming out. This is 15 months after this filter was installed. There's no maintenance on these filters. So if you were a teacher, would you want to prepare lunch with that, or would you want to prepare lunch with that? Okay? And this is acknowledgments. This is an old picture. I need a new picture of my students, but I don't have that. So I've had lots of students and cooperators on this project. And so where am I going? I'm getting there. I may be an old dog, but I got rocket power.
Have you ever drunk the water that you've been filtering?
Not yet, because like I said, it has to be disinfected. So I would, because they boil it down there. But we also have some ceramic filters that are commercial. So when we go down this next time, we're working with EPM, which is a water company for Medellin. Medellin has got 2 million people in it, and they've got a government contract to install some sort of water treatment system in 2,500 schools in the Antioquia area. And they've started by installing treatment systems in large schools. They've installed them in 100 schools because their system is a Siemens system that costs $5,000. They can do it only in schools that have hundreds of students. They don't know what to do with these schools that have 20 students. So they're really, really interested in what we're doing, and hey, they can put it in 2,000 more schools. So we're taking a trommel down and we're taking some materials down to show them how to do it, and hopefully we'll be sending them more porous plates and everything else so that they can do this in hundreds and hundreds of schools in Columbia. So, but the idea there is if they chlorinate and then run it through the ceramic filter costs $80. So for less than $200, you can put a water treatment system in a rural school. Right now, they're boiling the water. They go through 1 tank of propane in about 2 months, and it costs them $30. So even the ceramic filter, if it lasts a year, it's cheaper than boiling all of that water. So our disinfection should be much more cost effective than what they're currently doing right now. And chlorine, 5 liters, 8 drops of bleach, and it's disinfected at 3 milligrams per liter. So it's very, very easy to bleach is just a hypochlorous or sodium hypochlorite, which is basically chlorine. It's just that it's at 5%, and you don't need that concentration. So just a few drops of bleach in 5 liters of water, and it's the same concentration that you're getting at the tap when you drink water in the labs upstairs or in the water fountains upstairs.
I have some questions from the students here.
You're supposed to ask me what am I supposed to do in the next 10 years, right?
Wait for the students to ask first, and you can tell us that. All right, go ahead and tell us about your future plans, Jan.
My future plans.
So there's in the slideshow.
Oh, what did happen? so more of this, and what else? And actually some more of this, because I'm currently working on a proposal with some people in agronomy on monitoring a pesticide in water the same way that we monitor the hormones. So that'll keep me busy for 3 years, right? And what other ideas do I have? Chlorine, so all sorts of things about chlorine. How do you measure it in rural areas around the globe? How do you dose it in rural areas around the globe? So how do you disinfect water when, because like I said, if you're in this country and you own a swimming pool, spending 15 cents to monitor chlorine a day is no problem. But when you're living on a few dollars a day, 15 cents is a big thing. So why are there not methods so that in rural areas you can measure the concentration of chlorine in your system or even dose it properly into your system? You got to get rid of the turbidity, and these sand filters actually do that quite effectively. So, there's a huge amount of work that can be done on developing countries. I've talked to people in China about doing this, and I'm actually going in March to Africa to talk to people about putting in some slow sand filters there to see if they want to do things in a larger scale. So that project's actually occupying a lot of my time. Right, too much of my time probably, right? The rest of my students think. But even the nanomaterials, they're not going away. And there's all sorts of, so graphene oxide, Ian Kahn's working on graphene oxide now. I didn't talk about that at all. I've had students that I've tried to get interested in degradation of plastics. There's plastics in the Pacific Ocean. If you Google that, even Wikipedia has stories on plastics in the Pacific Ocean. It's a huge problem. Why are these plastics not breaking down? And Professor Hua and I may even do some work on that together. What else? There's lots of things. It's just getting the proposals out the door.
Okay, great. We want to thank you again.